b. Cleaning this up now, we just do n plus 1 log base b of 10 is less than or equal to n prime plus 1. So n prime should be greater than or equal to the same negative 1 plus n plus 1 log dot dot dot. And if we take the, let's see, take the ceiling, yep, then we can say n prime, so n prime equals the ceiling of negative 1 plus n plus 1 log base b of 10. So I was way off, actually. My dumb little function here is not even close. So let's move this over here. This is 1 minus the multiplication of 1 plus n times the log of 10 in base b. And then we do the ceiling of that. So now let's see what we get back. Yes, that is way, way, way more reasonable. Way, way, way more reasonable. So we want to return both the base, the length, and why not the modulus. So, oops, we don't want to do wrong values. This ceiling is already going to be done for, so we can just do this. Great. Digits in base b, we can, this is going to be the result of let's do this, delete this. None of this is actually looping. That is a problem. We're not actually doing a search, so to speak. Clean this up. And now when we run it, we get this. So if we wanted, let's say, 9, let's see what happens if we do 10 billion. That's kind of curious. It's saying that there's only 32 additional terms. Something's fishy about that. Wait, let's go back and look at this. Let's see, 9 is 69200. Let's do 10. Oh, that's not 32 additional terms. It's 2 orders of magnitude larger, which is, well, an order of magnitude larger, which is correct. An order of magnitude larger in one base is approximately an order of magnitude larger in another base. So, this is really, really good. Let's write some documentation for this. So this function, to recap, computes three things. It computes maximal base in which arithmetic can be performed, required length of the transform, and lastly it computes so we have this. So let's interpret these results. I don't think I was very clear. If we want to compute 10 billion digit multiplications, what this is saying is that we need the base of our numerals to be this right here, which is what, 4 billion? Let's see, 1,000, million, billion. Yeah, 4 billion. The digits, the number of terms that we'll need to compute, not terms, but the number of digits, so to speak, in that base is going to be about 2 billion. Yep, 2 billion. And then our modulus is going to be this large number right here. No, this is not Clojure, this is Common Lisp. So what happens if we only had 60 bits? So this is saying that if we had 60 bits to do the exact same computation, our modulus is, for one, going to be smaller by an order of magnitude. The length of our transform just went up 200 million terms. And the base is now, smaller by an order of magnitude. If we were on a little old 32-bit platform, if we only had 32 bits to work with, then our base would have to be 40,000. The number of terms we'd have to compute would be 4 billion, I think. Let's see, 1,000 million, 4 billion, which I think exceeds the number of elements you can even address. And then our modulus would have to be this smaller number, which fits in a, let's see, yep, it fits. Next one. So for Lisp in particular, if we were to write performant code in Lisp, for a 10 billion digit number, we would have that. What about if we wanted to multiply two numbers that have, I don't know, 10 digits to them? If we have only 10 digits, we can use two terms. We can use this absurdly large modulus here. And we can work in this base right here. What about our little example that I've been speaking about where we only have 3 digits? That's clearly wrong. We need at least one term, so maybe I should say not this 1 minus right here. We need one term whose base is this huge number, and then whose modulus is this. So actually here we could probably choose a larger base, a larger factor of 2. But it doesn't do that. Let's see, on 32, Let's see. I use 32-bit on 64-bit platform. A multiplication of 232 yields 6. I'm not sure what you mean by not completely true. Oh, it's not true about your C implementation? Yeah, C does have 128-bit integer returns, but it needs to spread those across 2 different registers on a 64-bit platform, unless you're able to do all of your arithmetic in one of the extensions, like what, SSE 3 or something? I don't know which one, but even those I thought were mostly for floating point. So I think this can be refined, but I think this is a start of a function that we need that computes many of the important bounds that we need to do. So I'm going to see if we have a trillion digits. 10 to the power of 10 to the power of 12. Wow, surprisingly we can still do arithmetic. It's just our modulus is smaller. So kind of the upper bound for what people have computed is 10 trillion. With 10 trillion digits, what is our maximum width? EXPT 2 to the 62. Yeah, so we have plenty of room. But this is actually a lot more promising than I previously thought. Let's do a little verification, however, because it almost looks too promising. So the square of that is that. Something is a little bit fishy. Times that was square root. Yeah, that is fishy. It's very, very fishy. It's because it's a bug. In my computation here, where I'm supposed to do, where I say that the modulus must be greater than n times the base squared, this n has to be the n in this base. If you notice, I'm computing this base, where do I do it? I'm dividing by n in the incorrect. Oh. I think something is incorrect here, because the modulus should be less than the product of everything. So let's see. I wonder what happens if I do when less than, when the modulus is greater than times n square of b, so the base